application of equilibrium. Application of equilibrium in industry. Okay, so we'll take our first example. Our first example will be in the what? Let's say contact process. Okay, contact process. Okay, so we want to see how in the manufacture of sulfuric acid, how the knowledge of equilibrium helps industrial chemists to decide on the proper condition for the reaction. And so what's the chemistry behind the choice that they make in production of sulfuric acid. Okay, so your contact process basically is under sulfur. Haber process will be under nitrogen. So under sulfur, you talk about contact process. So I'm just going straight to the manufacture of sulfuric acid. So we'll look at the manufacture of sulfuric acid, then we'll now pick the equilibrium reaction there and explain the condition for the reaction. So the first thing under the manufacture of sulfuric acid is the fact that your sulfur is first burnt in air. You burn your sulfur in air to form what? To form sulfur dioxide. Okay, so your sulfur is first burnt. Sulfur is burnt, okay, yeah, in air to form sulfur dioxide. Okay, now the next thing that happens is that the product is mixed with oxygen to form sulfur trioxide. So you have further oxidation of your sulfur dioxide to form what? To form sulfur trioxide. You have further oxidation of your sulfur dioxide to form what? Sulfur trioxide. But that reaction, okay, the reaction is a reversible reaction. Okay, it forms sulfur trioxide. So it's a gaseous system. So you can see now where equilibrium is almost coming in. So we can see here, this particular reaction, the forward reaction is exothermic. The forward reaction, you need to note that, please. The forward reaction is what? Is an exothermic reaction. Okay, now so let's see how they arrive at the production of sulfuric acid. They will now come back to where can this reaction be controlled? Okay, where can it be controlled? So having produced your sulfur trioxide, which is this is your sulfur trioxide. Okay, the next thing done in the industry is that the reaction between sulfur trioxide and water is too violent to be carried out directly. Because to produce sulfuric acid, we need to dissolve your sulfur trioxide in water. Your sulfur trioxide is an acid and hydride. Acid and hydride are gases that dissolve in water to form acid. But to dissolve sulfur trioxide in water directly, it's very exothermic. I mean, it's a very violent reaction. So in industry, how is it controlled? So to control that, your sulfur trioxide is dissolved in concentrated sulfuric acid to form what we call oleum. So we dissolve sulfur trioxide, okay, in sulfuric acid. Sulfur trioxide in sulfuric acid to form what we call oleum. Don't forget that the essence of doing it this way is to ensure safety. Otherwise, we would have dissolved your sulfur trioxide in water. Would have dissolved your sulfur trioxide in water. Okay, that is your water directly to form what? H2SO4. It looks like a short way to do that, but it's a very violent reaction. This reaction is what? Is very violent. Of course, as you produce in industry, we want to talk about issue of safety. So they have to dissolve it in what? Concentrated sulfuric acid. This is concentrated sulfuric acid. And that gives us what? Oleum. So when that is done, then your oleum is now further dissolved in water. So water can now be added to your oleum. This is called oleum. Okay, so water can now be added to the oleum to form what? So when water is further added to the oleum, then you can now produce your sulfuric what? Sulfuric acid. So we can balance this. We can have 2 moles of what? 2 moles of sulfuric acid. Okay, so this is how sulfuric acid is produced what in industry. Okay, sulfuric acid is called a fine chemical. It has a lot of application in industry. So, but now, what is our focus? How do we link chemical equilibrium to what? To this particular reaction? How do we link chemical equilibrium to this? Our focus is on this particular reaction, because that is the only reaction that is a reversible reaction there. So we want to see how to control this reaction. For contact process, what are the conditions for contact process? What are the conditions for contact process? So let's write down that reaction is SO3 gas, okay, plus O2, okay. We said it's a reversible reaction to give us SO, sorry, that was SO2, sorry, SO2 to give us SO3 gas, okay. This reaction is a reversible reaction, and the forward is exothermic, delta H negative, XYZ. Okay, kilojoule per mole. Kilojoule per mole. So you can see there. Now, what are the conditions? Conditions for contact process. Conditions for contact process. Number 1, for contact process, it requires what? It requires a vanadium 5 oxide. Remember vanadium 5 oxide? That is the catalyst required for this reaction. Vanadium 5 oxide. Vanadium 5 oxide. So the reaction requires a catalyst. Okay. Then also the optimum temperature for contact process is around 450 degrees Celsius. That's the optimum temperature. And of course, atmospheric pressure. Atmospheric pressure. Okay. Atmospheric pressure. That's 1 atmosphere. That's atmospheric pressure required for this reaction. So we'll ask ourselves, what is the reason for optimum temperature? Because in industry, we know that increase in temperature can increase the rate of reaction. Increase in pressure can increase the rate of reaction. So wouldn't I want to produce my product very fast as a manufacturer? So why can't I just increase the temperature to something like 10,000 degrees Celsius so that in the twinkle of an eye, I can produce my sulfuric acid? So it doesn't happen like that in industry because there are certain things to look at. Okay, why can't I increase the pressure to very high pressure? In industry, again, it doesn't happen like that. We have to consider safety. We have to consider costs of manufacturing. Then we have to consider the yield. There must be a balance between rates and yield. A balance between rates and and yield. So rate means how fast, okay, the product is produced. Then yield means how much of the product is produced. So we have to find a balance. Sometimes when you increase the temperature too much, the reaction is going to be very fast, but you are going to produce less. That means you produce so less quickly, but you can produce more slowly. So can you get that concept? So in industry, we have to find a balance, a middle ground, okay, a condition that will produce my product at a reasonable rate and at a reasonable yield, quantity, that will meet up the expectation of my customers. Okay, so the reason for using optimum temperature for this reaction is because the forward reaction is what? Is an exothermic reaction, remember? So, okay, let's assume that I want to increase my temperature to like 1,000, increase it. What do you think is the effect of increasing temperature on rates? So let me put it together now so that we'll look at it in perspective. So we are going to be looking at 3 things here. We're going to be looking at rates, we're going to be looking at yield, and we're going to be looking at cost, because these are the things that you need to to put the perspective in industry. Rate, yield, and cost. Rate, yield, and cost. So if I increase the temperature, say beyond 450, say like 1,000 or 10,000, increase in temperature. So what is the effect of increase in temperature on rate of reaction? What will be the effect of increase in temperature on?
Sorry, supposed to increase the rate of reaction.
Okay, so increase in temperature will increase rates, right? Good. So now I'm happy in industry that, oh, my product will be produced quickly. So that's on one side. So what about the yield? The yield of this reaction, increase in temperature. What effect will it have on yield?
There's a reaction exothermic or endothermic.
The forward reaction is exothermic. The forward reaction is exothermic. So what effect will it have on yield?
So please repeat. I didn't hear what you said.
The forward reaction is an exothermic reaction. So what effect would increase in temperature have on yield of reaction?
So it will make the reaction move. It shift equilibrium to the left. So
Okay.
less CO3 is made.
Thank you. Thank you. So increase in temperature will favor the backward reaction, which is endothermic, right? Because the forward reaction here is what? An exothermic reaction, which will not be favored by increase in temperature. So that means if I increase the temperature of the system in an attempt to increase rates, what I'm going to get is I'm going to get less of sulfur trioxide being produced. This is sulfur trioxide. I'm going to get less of sulfur trioxide being produced, right? So that means I'm going to have a decrease in what? A decrease in what? In yield. Okay, yield of SO3. I'm going to have a decrease in yield. And a decrease in yield will not favor me because I need to produce more product. So it means the more I increase the temperature, the lesser the yield that I get. So you can see why in industry they can't increase the temperature too much. So they increase the temperature and they will vary the yield that they get. Okay. Now also, if I increase the temperature too much, it's going to give me high cost. Because to increase temperature means that I need to supply energy, heat energy. Maybe I need more heater. I need to use more coal. I need to produce more source of heat energy. And that simply means I need more cost to be able to bear that energy cost. I want to spend more money. So can you see that? So the more the temperature that I need, the more the heat energy that I need, the more the cost, okay, of producing my sulfuric acid. So in industry, they have to come to a temperature that is not too high and that is not too slow. I mean, not too low, because we need a reasonable rate of reaction, right? Now, let me paint it this way. Let's assume that you chose a temperature of 10 degrees Celsius, okay? And it took you 2 months to produce your product. Let's say you are producing Indomie, for example. It took you 2 months to produce that, okay? And you got a yield of, let's say, when you use 10 degrees, you got 10 cartons. You get 10 cartons, okay? Or let's say 10 packs. Let's say you got 10 packs, okay? That's what you got at let me just look at rates and yield, just rate and yield first. So then I increased the temperature to 50 degrees Celsius. It took me 1 week, and I was able to produce, let's say, 30 packs. Oh, sorry. Since it's going to be, my yield is going to decrease, right? Don't forget, increase in temperature will decrease my yield, isn't it? So I was able to produce 8 packs. 8 packs, okay? I was able to produce 8 packs. Then I increased the temperature to 200 degrees Celsius. It took me 1 hour. 1 hour, okay, to produce, or let me make it fair. It took me like 3 days. 3 days, okay, to produce 6 packs. Okay, so if you are the consultant, for Dangote industry, okay, what temperature would you encourage them to be using for the production? What temperature would you encourage?
So maybe 50 degrees.
Maybe 50. Why?
So like it's making in 1 week 8 packs, but like in water it's making in 2 months 10 packs. I feel so like it's a bit more economical to do 50.
Okay, it's more economical to do 50, right? Because
Mm-hmm.
if I was to produce, 10 packs in 2 weeks, I mean, I want to increase my rate of reaction. Okay, so I increase the rate to 50 because increase in temperature increases the rate of reaction, right? But I also noticed that because the reaction here is exo, increase in temperature will reduce yield. But the reduction in yield is just 2 parts, right? Good. And it gave me 1 week. But okay, and that's okay. If that is the case, let me see if I can increase the temperature further. Now I increase the temperature to 200. I found out that in 3 days, okay, in 3 days, I was able to produce what? 6 packs. Okay, so would that be okay for me, knowing fully well that if in a week, if I double this in a week at 200 degrees Celsius, in a week, I'll be producing 12 packs at 200 degrees Celsius. Okay, but my temperature here is 50, and the amount of energy that I will consume to produce 50 temperature is far less than the amount of energy I'll produce. So let's assume that this one costs me 2 million naira to produce this energy. Okay, and this one costs me just 500,000 naira to produce 50 kilojoule. So I would rather go for 50 kilojoule, 50 degrees Celsius, okay, than going for 2 million naira. Because by the time I do this in 2 weeks, I will have 16 packs. 16 packs, and I would have spent 1 million naira to produce 16 packs, other than spending 4 million naira to produce 12 packs for at what 200 degrees Celsius. Can you see how they think in industry? So when they tell you this reaction in industry takes this temperature, this pressure, you're wondering what is the essence of that? Those are the things that they put together, okay, before they come to that decision. So when somebody say I'm an industrial chemist, this and many more, okay, are what they do as consultants in the manufacturing world process. Okay, so you can see here how they arrive at this condition. So we call this condition state of work compromise. Compromise means you think about it towards the left, you think about it towards the right, and you arrive at a what? At a compromise and say, okay, we think that what? Manufacturing at 450 degrees Celsius, 1 atmosphere, and using catalyst is better for what? For us. When you consider rates, when you consider yield, and when you consider what? The cost of production. Okay, so this is the application of chemical equilibrium to what? To contact process. I hope you got that.
Yes, I did.
Okay, so if you look at this, there will be no need to increase the pressure to to too much, because I may want to be tempted to increase the pressure. I say, okay, if you look at this system, increase in pressure, let's look at it. Increase in pressure will favor what? Where will it favor? Forward or backward? For this reaction, increase in pressure will favor what? Forward or backward reaction?
Sir, to favor so to favor the forward reaction.
About the forward reaction, that means increase in pressure, right? Okay, increase in pressure will do what? Will increase rates, isn't it? It will also increase my what? Yield, right? Increase in pressure increases rate of reaction. We know that. For this particular reaction, increase in pressure will increase the yield of SO3. So now it look as if I will be tempted as a manufacturer to keep increasing my pressure. But the truth is, the more the pressure that I need, the more the cost. Okay, because if I want more pressure, I will need thicker pipe in industry. I will need thicker pipes. I need thick pipe to work to sustain the pressure. Otherwise, my industry will blow up. Okay, so I need the pipes to be stronger pipes. So the more strong, the thicker the pipe that I need, the more the cost that it will cost me. So those are the things that they look at in industry. So, okay, this pressure is okay. After all, we are using a catalyst. So the catalyst will help to increase the rate. If pressure, we don't have the advantage of pressure and temperature in this particular reaction to increase the rate of reaction. So let's include the catalyst. Catalyst will take care of the rate of what reaction. Why we focus on what condition that will give us, that will maximize yield of reaction for us. You got that? Right?
Yeah.
Okay. So the next application we'll look at, which will be the last application, will be Haber what? Haber process.